Hi, welcome back to Educator.com. This is the lesson on origins of life. So first we got to talk about where Earth came from, because that's where life as we know it exists. So a brief history of Earth. It's about 4.5 billion years old, and I put a little approximation symbol there because depending on what source you look in, what textbook, some may say 4.45 or 4.48 or around that time. So about 4.5 billion years ago is the age of the Earth. Formed from a coalescing of matter into a spherical form. I won't get into a lot of detail here. You could take an astronomy course, astrophysics course, that could explain more details about that. But after the Big Bang, after the universe originated, you had a lot of matter coming together in different ways, forming the galaxies, forming stars as we know them. And for the Earth, you just had this what is natural for matter to do coming together in a very spherical form. But at first, it wasn't the Earth as we know it. It wasn't this blue planet with lush green life. No, it started off as a fiery ball of hot volcanic activity. In its early stages, as far as we know, just all kinds of magma coming up through the surface, just very hot and just full of volcanic activity. Now, volcanic activity still exists today. I don't want you to think that it completely ended. There's always volcanic activity happening in various places on Earth. We just don't hear about it all the time. But if you look into it, there's still quite a lot of volcanic activity. Back then, in Earth's early years, eventually you had enough cooling, enough, in a sense, calming down of that frequency of volcanic activity to have a crust. So there wasn't a crust at first, but eventually the lava cooled enough to create it. And once you have land, once you have something that's a little bit more stable and cooler, you can then have some more steps leading towards life. Like I said, magma still exists underneath, plenty of it, and volcanic activity is continuing worldwide. So here's an image of that volcanic activity. Speaking of volcanic activity, all of those eruptions, all of that spewing of gas from the Earth's surface created an atmosphere. Because of the Earth's gravitational pull, that contributed to a lot of gases hanging around. So we have this atmospheric layer, actually several layers, around the Earth's surface. Compared to the Earth itself, in terms of the Earth's diameter, the atmosphere is actually quite thin. I've heard it described as like if you had a globe and you put like some lacquer finish on the outside, that's analogous to how thin the atmosphere is to the actual diameter of the Earth itself. But the question is like, hey, what kind of gases did we originally have on Earth's surface? So the key to knowing about Earth's early gases is what came out of volcanic vents? What came out from those volcanic eruptions? And if today you were to go to where a volcano is actively erupting and you use some tools to measure, hey, what levels of what gases do we have coming out from this volcanic activity? Here's some of them, not all of them, but you would find carbon dioxide, water vapor, nitrogen gas, hydrogen sulfide, methane, plenty of other ones. And I didn't list them all here. There's actually a few other ones that I list on the next slide when we talk about Stanley Miller and Miller-Urey. This little group of gases here does not support life. So the first atmosphere on Earth, and actually for a while, wouldn't have been able to support modern day animals, let alone most life forms on Earth. It would be toxic levels, not enough of the gases that support life. Speaking of not supporting life, this is not actually Earth's breakdown of gases. This is what we know as Mars' atmosphere. So check it out. Almost all the gas is carbon dioxide. You might think, oh, well, plants, they could get by. Well, this is actually too much CO2 level for a plant. You got argon, nitrogen, oxygen, and carbon monoxide. Carbon monoxide would be one of the other ones that you would find Earth's early atmosphere. That is by itself toxic. So anyways, gases from this time contained the elements, the building blocks for organic compounds. If you look at what you got here, we've got carbon, oxygen, hydrogen, nitrogen, sulfur. get some phosphorus in there, a few other things. You've got all the building blocks you need to make cells eventually. Think about it. CH&O, that's in every organic compound or molecule. Nitrogen, you would find in nucleic acids and proteins. Sulfur, you definitely find in particular amino acids as well, in proteins. So those building blocks are there, just not in the right form, not in the right combinations yet. So how do you get from inorganic gases to organic compounds? How do you get from gases that are not the building blocks of life to the building blocks of life? The answer to that question from the previous slide is Stanley Miller and Miller-Urey's experiment. So the Miller-Urey experiment from 1953, these two scientists demonstrated that you can get organic compounds from inorganic starting materials. Here's how they demonstrated it. They had a setup with gases, these are among them, from early Earth, like we talked about in the previous slide, in a glass container, this little spherical container here, with electrodes attached to it, so you could zap them. And that's supposed to replicate lightning. So if you imagine having these gases in Earth's early atmosphere and getting enough water vapor up in the atmosphere, you could get lightning storms. And the theory was that maybe over time, lightning zapping these gases could have kind of made a lot of these elements get mixed up in different combinations because of that electricity. So they wanted to demonstrate that it's possible. They have kind of a replication of ocean here with water, a heat source. You're of course going to have that heat source from hydrothermal vents, from vents that heat the water. And there's a lot of theories about how early cells may have come into being in these little like hot pools in the ocean. So you have heat here, you get some water vapor coming up into here, you create basically kind of a little mini atmosphere there with lightning. You've got a condenser here, cool water wrapped around this particular tube. That can encourage these gases to end up coming down into the liquid. And the interesting thing is, after they zapped these gases repeatedly, they found what was sterile water in here, just water with no organic compounds in it. They found amino acids, among other organic compounds. They proved it's possible, that if you zap these gases enough, you can get them rearranging in interesting combinations like an amino acid or a simple sugar, perhaps. So yeah, the amazing thing is they proved it. The year it happened, 1953, overshadowed by another very famous discovery, the double helix structure of the DNA from Watson and Crick. But I think that the Miller-Urey demonstration is equally as important.